This is the second unit on KVL, and we are going through a slightly more complex problem than we did the first time around. The issue is not in understanding the idea behind KVL, and for that matter KCL, but in applying it. In other words, as the systems you will be studying become more complex, how do you identify the loops and track all the voltage drops around the loop? You will have the opportunity to observe in this section that it is not necessary to use all the loops in order to solve the problem, but it is necessary for all the loops to conform to KVL. Now I have given you, on the bottom you can see that I am giving you certain voltages in the circuit. At this point it is not clear where those voltages are defined, but still take some time to study the circuit. And in this case, I am defining the nodes for you, A, B, C, and D, and I'm also defining ground. In other cases, you will have to define the nodes, and you should always remember to save one of your nodes and define that as ground. So once I have defined the nodes for you, then if I'm giving you VAB equals 5 volts, you know that the voltage from A to B is equal to 5 volts. And in this instance, because the only component between A and B is the component C1, I'm giving you the voltage drop across C1. In the same way, VAD is the voltage drop across C4. VBC is the voltage drop across C2. Now, VBC is defined as B is the high and C is the low. So if I write VBC, then the plus has to be on the B side. If I had written VCB, then that would be the voltage from C to B, and I would actually be reversing the polarity of the voltage, so the plus would be on the C side and the minus would be on the B side. So you do have to name your voltage drops consistently, and you have to assign the polarity in a consistent way. So note that VA across component C7, VD across component C6, and VC across component C8 are node voltages. And so VC looks like I have labeled it inconsistently, but I haven't. The plus side of my voltage has to be on the side of C. Now define the loops in your circuit: loop 1, loop 2, loop 3, and loop 4. And you can define more loops. You could define this as loop 5 and any closed loop in your circuit as a loop 6, a loop 7. You don't have to define any more loops than you need to solve for the voltages in your circuit. So we will use these 4 and see if they're enough to solve for the other voltages. So I'm going to write the KVL equations for these 4 loops. And if you take the time, let's take the time to just look at loop 1. I'm going around in a clockwise fashion. The arrow on the arc that I've drawn inside the loop shows in which direction I want to go. So when I'm walking in that direction and I hit C1, then I hit plus first and then minus. We've already defined that as a voltage drop, so I'll put minus VAB. Minus VBD, and then VAD, when I hit C4, going clockwise, I hit the minus first and then the plus, so that's a rise. So then I add VAD, and that's equal to 0. Loop 2 is VBD minus VBC plus VDC is equal to 0, and loop 3 and loop 4 are consistent with that direction of motion. Now, see if you can identify which loops these equations would correspond to. And if you print out this page, you can even draw it on the circuit just to see if your understanding of how to go around a loop and how to add up voltage rises and voltage falls is correct. Again, as you go around the loop, you've drawn a loop with a direction in which you're going to follow that loop in there, so be consistent with how you follow that loop. Okay, so you have your loop 1 through loop 4 equations. Let's take the time to identify which voltages I know in these equations. I know VAB, VAD, VBC, and VC. These occur in the different equations. And so I substitute the known values for those symbols. And please, for loop 2, note that the minus 10 volts, I'm putting it in parentheses. You could directly say that that's VBD plus 10 volts plus VDC. What you can't do is put VBD minus 10 volts without putting the minus 10 volts in parentheses. That's not correct notation. Note always that note as well that I always record the units, and that is important for several reasons. It is important because it is the right thing to do. I need to know, and you need to know at any point in time, if you're adding voltages, if you're adding currents, if you're adding resistors, the unit tells you what sort of physical parameter it is you're putting in the equation. Besides that, the units are used to check your work. If at the end of a complex process you calculate a current but your units are in ohms, then you know you've made a mistake somewhere, so you go back and try to find what that mistake is. If you've been consistently using units all the way through, it is easy to troubleshoot. Now, again, look at your equations and try to find the equation that gives you the most direct the most direct solution. So loop 1, you know 2 of the voltages in the equation, and you need to calculate the third. So obviously you'll start from loop 1 and calculate VBD is equal to 2 volts. And then you substitute VBD into whatever other equation it is found in. It is only found in loop 2 at this point. So loop 2 now has 2 volts plus 10 volts plus VDC is equal to 0. So it's easy to solve for VDC. VDC is equal to minus 12 volts. Again, you substitute VDC wherever it is found in the remainder of the equations. Loop 4, if you substitute VDC in there, the only remaining unknown is VD. So VD is equal to minus 6 volts. And then you substitute VD into the loop 3 equation and calculate VA. So we did start from loop 1 and go to loop 2, but then we jumped to loop 4 because that was the equation where it made sense it made sense to work with next. Okay, so take the time now to write your results in there. And you see that as I was writing the results, the voltages on my circuit, I changed them from black to blue. And I look at my circuit and I see now that I have, in fact, solved for the remainder of the voltages in the circuit. How do I check my work? Well, I go through loop 1 again and I substitute the known voltages. Minus 5 minus 2 plus 7 is equal to 0. That's a check. Minus 10, which is plus 10, minus 12 plus 2 is 0, minus 7 plus 6 plus 1 is equal to 0, 12 minus 6 is equal to 0, and I also check some of the other loops. So if I go around loop 5, will I have a check? Yes, I do. Minus 5 plus 10 minus 6 plus 1 is equal to 0, so that's a check. And if you're still not convinced, feel free to go around any loop in the circuit and make sure that KVL is satisfied.